Hi, my name is Jordan Smith, and today we'll be talking about projectile motion. Once again, we're using our fundamental principle, the momentum principle. The momentum principle states that the net force is equal to the derivative of momentum with respect to time, or after using a bunch of algebraic techniques, we realize that it's also equal to mass times acceleration. Here's our original video modeled with tracker data. Provided here is our tracker data, which will allow us to find our initial position, initial velocity, and delta t time step. Provided here in this slide, we're given our initial conditions from tracker. Our initial time was at 0 seconds, each time step being 1 over 33 seconds. Our ball's mass was 0.0052 kilograms, or 5.2 grams, and we're given our initial position and our initial velocity, which is 1.879 meters per second in the x component, 2.473 meters per second in the y component, and 0 meters per second in the z component, of course. Slide here, we're implementing the momentum principle in VPython. Below are all the initial conditions that we saw before, and we're also implementing the momentum principle. For velocity, that states that the ball's final velocity is equal to its initial velocity plus F net over m times delta t. And for the position, the final position is equal to the initial position plus the velocity times time. Now we're about to implement all that VPython data and run all the data here shown inside of my idle shell. And there we go. Now, in this slide, we have two graphs. One graph noting the x position with respect to time from tracker, and the y position with respect to time from tracker. This slide here, same thing, but instead of using our tracker data, we're using our computational model data. But as you might notice, the y position is a bit off, while the x position is somewhat keeping up more. To understand what could be going on, we need to introduce a new fundamental principle that we'll be using specifically for this lab. Introducing our second fundamental principle specifically for this lab, drag force. The drag force is equal to negative b v squared times v hat, where b is the drag force proportionality constant, v is the magnitude of velocity, also known to most of us as speed, and v hat is the unit vector of velocity. This force is proportional to the square of the object's speed and points opposite to the motion of the object. You may be wondering, how are we supposed to calculate the proportionality constant? Honestly, you'll just have to kind of take a few guesses, and for me, I did a bit of research. I found that the drag force of a uniform sphere is usually equal to 0.47, and then I also tried to take into account the roughness of the paper ball. Although I'm not sure if this will make it higher or lower. We'll see in the next slide. After a lot of trial and error, the closest number for the constant I was able to find was 1 times 10 to the negative 6 plus 1 times 10 to the negative 12. Here's a video of us running our model with our brand new drag force right here. And there we go. Once again, here's a computational model B graph with the data already being ran. Same as before. Now, here's a comparison of all three graphs. As you may notice, model B is still not as accurate as we want it to be. But why? Why is our model still in error such a large amount? A possibility is that there's some type of lift force. From the moment in the video where the ball was lifted, there was already an uncalculated force that was playing a significant role in our tracker data. From this, we can also conclude that we never reached terminal velocity, as the lift force continued to play a role even until the very end. Now, we're given this what-if scenario. Imagine if the object were initially thrown straight up, with the same initial speed as our experiment. Would the time the object take to reach the ground be the same, longer, or shorter than it took in our original experiment? I decided, let's run a computational model with these exact conditions. Here's the computational model here, with our calculations of the magnitude of v and our test velocity as well, with everything else staying exactly the same. we're able to conclude that it'll actually take less time for it to reach the ground than it did last time. And that's it. Thank you for watching.